Hey guys, you're watching Python tutorial videos on my YouTube channel, Python for Microscopists. In this video, I'm going to talk about generative adversarial networks, or GAN. And in the next tutorial, let's actually implement what we learned today in Python. Now, GANs are very highly researched even as we speak, and this is mid of 2020. And the application space of GANs is ever increasing. So it's, I should say, in its infancy right now. So it's very important for you to actually at least get familiar with what they are so you can figure out whether this helps solve your research challenge or whatever challenge you're trying to solve in the field of image processing or data analysis. So let me actually start this by talking about the terminology here. We call it generative adversarial networks. Well, let's explain the terms one by one. Generative, part of this method actually, as the name suggests, it generates data, which means it's actually creating fake data. Here, there is a fake data of an outline of Mona Lisa. If I actually trained it for a lot more epochs, I could actually generate something that looked like real Mona Lisa picture. But the whole point of generative is it generates data. In fact, the primary application of GANs is generating fake data that looks realistic enough. Okay. Now, the adversarial part comes from the point that the generator and something called discriminator are competing to win. Discriminator, think of it as our regular machine learning algorithm. What do? We try to, for example, classify a pixel for semantic segmentation. Or if it is an object, like you're trying to classify cat as cat or dog as dog, right? So that is discriminator. You're trying to discriminate there, okay? So think of generator and discriminator competing to win. Meaning, as I mentioned, generator is trying to fake the data and the discriminator is trying to say, no, that's fake data. That's not true, okay? That's discriminator. So which means now generator is like, okay, the discriminator caught me. Let me go ahead and get better in the next epoch. And the discriminator also gets better. So they both compete to win, and then they both develop as we keep training these two algorithms. Eventually, there comes a point where generator is good at generating images, fake images that look realistic enough where the discriminator cannot discriminate, meaning the probability of that image being a fake or real would be 0.5, right? It doesn't know which one it is. That's when we know that, okay, this is a great generator that I can use to generate more images that are realistic looking, but they're fake. Okay, so that's the adversarial part. And networks, as you probably know, network stands for network. So the network can be deep convolutional. The network can be fully connected, or meaning dense layers only. Okay, so I hope you're versed enough in terms of neural networks so you understand what I'm talking about here. If not, please watch my earlier tutorials about, UNets or other deep learning videos as part of this channel. That reminds me, please subscribe to this channel right now. Pause the video, subscribe it. It really encourages me to learn more about these type of things so I can teach you about it. Okay, so now that we know what generative is, what adversarial is, and what network is, let's actually go down and let me explain the architecture of these GANs. So every GAN, you supply a random seed. It can be a one-dimensional, it can be two-dimensional, but you supply a random noise or random seed or latent vector. If you look at other videos on YouTube or read documentation online, you see these terms. That's why I'm including both here. Latent vector, random noise seed, or whatever it is. This is basically a noise that goes into the generator network. And the generator network can be convolutional network. It can be dense layers only, like fully connected network. Okay. So this random noise, let's say of dimensions 100, okay? I have 100 by 1 noise vector, or a NumPy array of size 100, okay, by 1. It goes into this generator network, and then the network can upscale this to create a two-dimensional image, okay? And on the other hand, I also have real images. So I have fake Mona Lisa images and I have real Mona Lisa images. And initially the fake Mona Lisa images don't even look like Mona Lisa. They look like noise, right? Because what we are supplying is noise. And as the learning goes by, it gets better. So somewhere in the middle, it looks somewhat like this. After, let's say, 50 epochs, it looks like this. But real images are real images, right? I mean, you actually have a very good definition. So both of these go into the discriminator network. Okay, so the first generator network, and then it goes into this discriminator network. And discriminator doesn't know if this is real or fake, and it's trying to sort them as real or fake. Okay, so it goes through. So initially, it gets trained, the discriminator network, on these images. So it kind of looks at, okay, hey, this is Mona Lisa, so this is a real, and this one definitely not. Okay, this is a fake. So as the network training goes on and on, of course, we are looking at the discriminator loss and generator loss, and then closing this loop, and then training the generator and training the discriminator, and this goes on for how long? How many ever epochs you actually define. Let's say I define 30,000 epochs, it goes through this loop 30,000 times. So think of this, two networks, one generator, one discriminator. So you're trying to train these two, which means you need tremendous computing resources, definitely a GPU. Okay, and I'm going to show you an example with, again, MNIST dataset, but if you really want to work with real life images, then you definitely need a lot of GPU for sure. Okay, so what are the 5 steps of actually training this GAN? Like step number 1, define the architecture based on the application. If the application is, let's say, super resolution, generating higher resolution images, based on low resolution images, then of course you need to work with convolutional neural networks. Maybe take something that already exists like VGG and then build your GAN architecture using those. Okay. Now, once you define the architecture, then we have to train the discriminator first to distinguish real versus fake. Okay, so now you have your discriminator trained to say, hey, this is real, this is fake. Now train the generator to fake the data that can actually fool this discriminator. Okay, and then you repeat this steps 2 and 3. Continue this discriminator and generator training for a few epochs, again, few thousand epochs, I should say. And at the end of it, what do we need? Well, if your goal is to create fake data, whether it is fake images that don't exist, images of people that don't exist, or high resolution images, or colorized images of black and white, or whatever the application is, most of the time for GANs, we are interested in generator only. We're actually looking at getting the, training the generator to make it better at faking the data. Okay, so that's why we save the generator model and to create new and realistic fake data. Now, one thing I should remind is when training this, okay, for example, when training the discriminator, hold the generator values constant. You don't just do this continuous together, generator and discriminator. So when you're training discriminator, the generator values are constant. And when training the generator, the discriminator is constant, okay? Each of this should train against its adversary so they can get better. Okay, so now a few applications. I already mentioned about a couple, like, of course, if you generate fake data for augmentation of machine learning, for example, you're trying to do some sort of a machine learning based, image segmentation, for example, and you do not have a lot of segmented data or a lot of how should I say, ground truth data, then obviously there are many augmentation techniques, like you can stretch the image, you can rotate it, you can do all kinds of transformations. That's still valid. You should still do that. But if you want to generate fake data, you can also try GANs, in generating that. Now you can generate faces. A fun website to actually go to is called thispersondoesnotexist.com. They look so realistic. The people that this website actually generates, it uses GANs again to do that. It's pretty much fun. And image-to-image translation, text-to-image translation, super resolution is relevant to microscopy, image processing in scientific research, for example. If you have low-resolution images and you want to get higher resolution, you can always do that by actually again, using the same logic, your realistic images and versus the noise generated images. So super resolution and domain transfer is another example. I really would like to do this one day. I gave this as an example. By the way, this link takes you to a page. I'll try to share this as part of my description, but this takes you to a page that contains a lot of information about the applications of generative adversarial networks in general. But what I would like to do one day is have enough images corresponding to both light microscope and electron microscope, or wide field images versus fluorescent images. Yeah, so you have different modality images, and then actually train it on these. So there comes a point where when you actually supply a EM or a light microscope image, the system automatically generates an equivalent electron microscope image, which is high resolution. So again, a lot of research is going on in these type of fields. So it's still a very emerging and very hot topic. Okay, so finally, I'd like to end this by showing you this super resolution generative adversarial network to generate these high resolution imaging using the low resolution. So this is the network architecture. Again, if you are not doing research in this field, it's very difficult for you to imagine how the network architecture should look like. I believe in this case, they kind of took VGG network, or you can actually take the VGG network and create something like this. But unless you are very good at, at coding, at understanding these deep neural networks, especially GANs, it can be very challenging. It's not just putting together a network. The hyperparameters, tuning of these, for example, alpha or momentum or something else, there are a bunch of hyperparameters that you can tune, which loss function, for example. A lot of things go into developing this. So it's a lot easier for us to copy something that got published and then customize it for ourselves, for our application, rather than create something from scratch. Okay, so I hope you learned something from this tutorial. Again, please subscribe to this channel, and in the next tutorial, let's actually take this knowledge and try to put together a few lines of code in Python. In fact, I'll already write a bunch of lines in Python, whether I copy it from somewhere and some I actually adapt it. But let's go through line by line to understand how the implementation is done. Thank you very much for your attention.